Well, hello 403 people, and this is my makeup video for the ones that didn't show up quite so nice before. I looked at the first set of 3 videos that I had put on before where I did them against the wall on the computer. The computer may not have been beautiful, but it was still readable. The third video on the wall where I just had a single sheet of paper, I could read it, and I figure if I can read it, you should be able to read it. But the first one, I could tell I was writing letters, but I really couldn't see them very well, so I realized that one was not good. So I'm going to redo the first video. I'm calling the other 2 ones good, and if somebody disagrees with me, you can let me know, and I'll consider redoing that. But at this point, it's like about 4 o'clock in the morning, and I'm pretty tired. So I want to finish this and go to bed. So what we did is we were doing mesh analysis, mesh or loop. Mesh is a specific subcase of loop analysis. Mesh requires a planar graph, i.e. there's no loops that kind of jump over it. I can draw it all flat in a plane with no components overlapping. And in a mesh, no mesh should have any other mesh as a sub area. So I'm going to redo the one that I did there as best I can. Now, so this is kind of our first thing. We're going to consider just a single one here. This is just Kirchhoff's voltage law. We've got a current. I'm going to call this I1 because that's where we start off on the other one. And if you consider this, I've got a voltage input V, and then I have the drops minus the V1. Well, according to Ohm's law, V1 is just IR1, and then minus the voltage drop here, and Ohm's law tells me that is I1 R2, and then minus this one, which gives me minus I1 R3, and that has to be equal to 0. Now that's the basic source for it, and I can go through and I can at this point distribute out the I, and this is known, and this is known, and this is known, and this is known. I is the only unknown. I can solve for the one unknown in it, and if you do that, you will find that you get I1 is equal to V over R1 plus R2 plus R3. And that's kind of, fun, and we go, okay, wonderful, that's great. What happens if I have more than one of these? And that's what we're going to do on this kind of second half. Now, something you'll notice on this, there'll be something that looks actually like this as the basis of the next one that I'm going to do, because it's going to have a very similar geometry. I'll turn the page here. Okay, and you notice I have another notebook below that allows me to align it when I switch pages, so I don't have the problem I did earlier where this ran off the page and you heard me talking but couldn't actually see anything. So, alright, now we're going to build a slightly larger one. So we'll and here we go. So we've got R1, R2, R3, R4, R5, R6. So this is using the same convention I did before as I was going around. Okay, so now we've got this, and we've got different loops. So I'm going to do these color-coded. Alright, this is my I1 loop, and this will be I2. Alright, now given that, let me write the equations now for each of these individual loops as it goes on, and we'll kind of color code them as they go. So whenever I'm using I1, I'll do it in red, and I'll do I2 in blue, and I'll do the resistors in black. So for the first one that comes in, I have my voltage. I'm still starting here. I always start lower left corner of everything I do, so it's just convenient. I see a increase in my voltage, and I get a minus, and I'm going going to see something using Ohm's law, it will be through R1. But I've got my lovely I1 is the current that's flowing through it. And then I go on, next component, I'm going to see minus. But now the net current is actually kind of complicated. It's still flowing through R2, but my net current is actually, I see I1 flowing this way, but I have I2 flowing the other direction, so it's opposing it. Now, the net effect of that is, it's like there's a little bit less current flowing through here, because this is a current divider, and I2 is the amount of current that flows through here, so I1, the total original current, right, minus the amount that flows off here is what comes down here. So I1 minus I2 flows through here, and I2 flows through here, meaning the sum of those two currents is I1 minus I2 plus I2, just I1, the amount that flows in. That's the node law, and yay, math works out. Okay, so at that point, I come back down to this area, and I2 rejoins up with I1 minus I2, so I have my I1 again. So I'm going to end up with minus, and then I've got I1 times R3, and that has to equal 0. And the reason why I'm color coding this is I think it will make it a little bit easier to see when I put it into matrix form. I'm hoping anyway. Okay, now I do the same thing over here. I start on this one, I'm going to go through this loop. Now I2 is my dominant one. There's no initial voltage source. What I see is I2 flowing through this, so it's minus. And I've got, again, that same lovely little current situation, except now I2 is the direction I'm following. So I've got I2, and I1 is going the other way. And then we're on this next I see, now I just have just I2, and I'm going to get R4 times I2. That's the voltage drop through next one, and I'll have minus, with R5, and being lazy, I'm just going to put the resistances in, and each one of these has current I2 flowing through them, so that's the respective voltage drops. Through those two, sum of the voltage drops has to be equal to 0. Okay, so this is equation 1, this is equation 2, from the two different mesh currents that I have. I can now take these, and I'm going to regroup them into my red and my blue terms. I'm going to put the red terms first and the blue terms second for each equation. I'm going to rewrite 1, I'm going to rewrite 2. And I'm going to take V, which is a known, this is a known, and all the stuff in black is known. The red and blues are unknown, and it's good to know what it is. This is a term known all by itself. I'm going to take it to the other side. So what I will end up with on this, I take it to the other side, and I'm going to go through and distribute all the negatives. I just multiply both sides by negative. Those are zeros, so it just cancels out, so I don't have to worry about it. And then when I take this to the other side, I'll get a positive V. It just makes it a little prettier. Okay, so for each one of these, I'm going to put the I1 terms first. So I'm going to grab every one of the resistances that has to do with I1. On the first one, it's R1 and R2 and R3. And in the second equation, I only have minus R2. There we go. And then I'm still going to kind of just leave the space so I can do that. And I got I2, I2. Alright, now I've got the I2s. Now I need the resistances that multiply them. Well, up top, I2 only appears here, minus R2. And I have on the other side equals V. I took it over. On the bottom, I've got I2 multiplies R2, R4, R5, and R6. So I get R2, R4, R5, and R6. There is no actual net voltage help going on. in essence, this one is getting all of its power from that current divider, or you can think of it as this coupling resistor, whichever way you would like to view it. Either way is acceptable and can be kind of taken from it. I'm going to pull this out so I have it to reference as it goes. Now I'm going to try to slide this down so I've got these equations here. And then I'm going to try to rewrite this into matrix form now. Now, when you're writing a matrix going on for the resistances, we're going to write it in a sense of Ohm's law. And in our case, it's going to end up being, let me pull this down a sec so I've got a little spot. You're used to the equation V equals IR. Well, in matrix form, I'm going to write this slightly different. I'm going to write RI equals V. The reason why I'm going to do it, if you notice that's going on here, I've got all my R's, here's my I's, and on the other side I have my voltages. This has a voltage in it, and this has no voltage source in it. So I've kind of written this in that form. Now you might say, hey, your I's are still first. And when I write it in matrix form, it's going to have the R's first. So that's why I'm going to put the R's first. Alright, so that's kind of giving you an idea of where my form is going. That should hopefully be visible to you. So now we're going to come over here and write this down. Now, when you have your matrix, each row corresponds to an equation. Each column will correspond to a variable. So the variables, the unknown ones that I'm trying to solve for, first is I1. So I might have kind of the I1 column. And I'll put I1 up here, just to remind you that I'm grabbing the terms that relate to I1. The terms that relate to I1 in the first equation are just this right here, R1 plus R2 plus R3. And the ones that relate to I1 in the second equation is just minus R2. Now, second column relates to second variable, which is I2. Now, this is not part of the equation. I'm just writing that there. This is a comment line, right? So this is just to remind you that the second column is due to the second currents, and I write the resistances. I get minus R2, and then second row is second equation, and I put in, and I've got R2 plus R4 plus R5 plus R6. Now, that is my resistance matrix. In order to get it that I1 multiplies the first and I2 multiplies the second, I have to have my currents afterwards. This is why I have Ri is equal to my voltages, which will be V0. That's kind of my voltage. So I get kind of an Ohm's law type thing going on here. And the second column, which is right here, and my first column is here, and this multiplication will now regenerate those equations. Nice thing is that this can now be written into matrix form, though, and put into a solver like MATLAB, and it's pretty straightforward to then generate these. And once I've generated them, I can solve for the i's by, if I call this, this is AX equals B. So if I define this matrix in MATLAB notation and this vector, I can then just solve for it. And I'll just assume I've got the R and V here. And I can just say that I is equal to R backslash V. Or if you like calling this AX equals B, that's just X equals A backslash B. So there you go. That is how to do a simple mesh equation. Hope that helps, and this is a little more readable. See you on Thursday. Bye.